Okay, today we're going to continue with waves, and we're going to look at the speed of waves and a few other details, but we'll start with speed. And the key thing is the speed of a wave doesn't depend on the amplitude or the wavelength, but it actually just depends on what the wave is traveling through. So if it's traveling through air, it's going to travel faster than if it travels it'll be different depending on the type of air, like if it's dense or thick or moist or dry, or even if it's in water, or if it's in a solid thing like a rope or a spring. All of those things will affect how fast the wave goes. And basically our formula for speed is quite simple. We just modify our old velocity equals distance over time. But in this case, instead of our total distance, we're just going to do the time or the distance for one wave. So remember, when we do one complete wavelength, so if we go from crest to crest, that's our distance. We're just going to use that as our d, and then instead of time, if it's only we're looking at one complete cycle, remember that is periods. We're just going to change it to period. So we actually would get velocity would equal wavelength over period. And we're also going to use the fact that frequency is 1 over period, and we can rearrange that a little bit and substitute it in, and we end up getting velocity equals frequency times wavelength. So that's our main formula we use for all of waves, and it's really one of our only formulas that we use when we're dealing with this. So let's do a quick example. So if we have a frequency of 6 hertz and a wavelength of 24 centimeters, we're going to try to figure out our speed. So our frequency is 6. Remember, that's in per second, so that's good. And our wavelength's 24 centimeters. We're going to want that in meters. So that'd be 0.24. So we just simply multiply 6 times 0.24. So pretty easy calculation. And we get 1.44. So that means the speed of that type of wave, in this case a water wave, would be 1.4 meters per second. So just like anything else we've been doing, make sure we track our units properly in meters and seconds, things like that. And I guess in this case we could even round it to 2 sig digs. So we'd get 1.4 would be good enough. So here's another one. Here we got the speed of light in this case, and it's asking us to calculate our frequency. So if we rearrange our formula, we'd have velocity divided by wavelength. So our velocity for light is 3 to the 8th, and we'll deal with that next year. But we can still do the question, and it's asking frequency of red light, which has a wavelength of 700 nanometers. Remember, nano is to the -9. So if we go 3 to the 8th, so we do 3 to the 8th divided by 700 to the -9, we end up getting 4.29 if we round it off, times 10 to the 14. So if we do this to 3 sig digs, looks good, and our units then would be meters per second divided by meters. So we end up just getting the per second, or our normal units for frequency would be hertz. So that means if we had a red laser, that's how fast that those waves would be getting pulsed at, or basically created at. We'd have 4.29 times 10 to the 14 waves per second. So super fast. That's why we don't see light as being a wave so much. We just basically see it all the time because it's moving so quick. So what we're going to look at now is what happens when waves hit boundaries, or they change from one medium to the other. So we already said the speed depends on the medium, so that means the actual wave is going to change. If the speed change, that means the wavelength is going to change. The frequency, or what causes the wave, doesn't change. So if you hear sound, whatever's creating the sound, let's suppose we have a siren, we're going to hear that siren the same unless it goes through a different medium. So you're inside your car, or it's a hot day or cold day or whatever, you would hear that sound differently. Or if you're underwater and you hear a noise, it sounds differently. So the frequency doesn't change, the source of the sound doesn't change, only the wavelength would change. So when we look at our formula, if our velocity changes due to the wavelength, you can see our f stays constant. So those two things will go up and down accordingly. So if we make our velocity faster, that means our wavelength will get larger, or velocity slower, wavelength gets smaller. So there's a few different things we need to remember. So one is when you have something go from a low density to a high density change. So the easiest way is to think of it as a wave hitting something solid. Obviously it's a lot more dense. So in this case, if we have a wave pulse going down a rope, when it hits the wall, some of that energy actually goes through. So we can kind of keep that wave going through the wall slightly, right? And more solid it is, less is going to happen. And then the rest of the energy gets reflected back upside down. Okay, so even if the wall wasn't solid, like suppose like we were going to just another rope or something that was even more thick, so let's suppose we got this and we're just going through like a thicker density rope, what would happen is when that wave comes, so the wave that goes through will still be going through forward. Let me just kind of erase this one. Okay, so it's going to go through the rope, and that rope will continue upright, so that would be sort of the same direction, and then the portion of the wave that gets reflected would still be upside down going backwards. And the size of those waves just depends on how efficient the transfer is, what the density is, and so on. So here's another video you can watch if you click on the notes. So this is basically just the guy has a wave machine set up and it's just hitting the end. So you can see in this case the wave is upright. When it hits the wall over here somewhere, it reflects back the opposite direction and it's upside down. So now what happens if we have the reverse? If we go from high density to low density, what happens is the wave actually reflects back again, but it comes back in the same format. So in this case, if it was air, like so we have this wave coming and it just hits basically nothing but thin air. When it hits the end of the rope or whatever it is, when it comes back, it actually comes back right side up. So it's kind of a strange one. Most people think, well, that doesn't seem right. But if you actually watch videos or you create one of these, it will do that. And again, it doesn't have to be just going into air. It could be hitting another spring. So again, if we had like our thick spring with a wave on it, and it's going to connect to one that's skinny, what would happen again is the skinny part, the wave would continue in the same direction, and then our thick part, the reflected portion, also is upright. So low to high, like a wall, it comes back upside down. High to low, it comes back right side up. And again, here's a couple more videos you can check watching both of these situations. So go to the notes and you can check this out. And that's it for today.